Great to have you here. I'm Ed Lazowska, and it's a complete honor to introduce the first of our distinguished lecturers for the 2018-19 academic year, Professor Margo Seltzer from the University of British Columbia. Margo was an undergrad at Harvard, a Ph.D. at UC Berkeley, where she worked with Mike Stonebraker. Her big project at that point was the Berkeley log structured file system, which I used to teach every year for many years, and lo and behold, log structured file systems are in these days, right? It makes a huge difference. The year she graduated, she was by far the most sought after graduate in all of computer science, not just computer systems, her field. Got offers from everywhere, and in the end was choosing between MIT and Harvard, and I think for a Harvard undergrad, having the president of Harvard phone you and say, we really need you to come try and rebuild this department was an irresistible lure, and that's exactly what she did. She played a major role in transforming Harvard into one of the nation's top computer science departments. But additionally, as a colleague of hers said in the Harvard Crimson, she's made the place human, and that's important and something we can all aspire to. This fall, Margo left Harvard for the University of British Columbia, so she's in the neighborhood now, and hopefully a great catalyst for collaborations between us and UBC. So take advantage of her presence, please. This is not quite Margo's title, but I don't want to spoil her thunder, so please welcome Margo Seltzer. Thanks for being here, Margo.
Thank you. What Ed failed to mention is that there was this one small school in Seattle that I didn't get an offer from, but we won't talk about that. When people ask me what I do, lately I have answered by saying, I do computer systems construed broadly. And so I want to take a few minutes before I get into some of the technical content. God, how did that happen? It does turn out that we have an alarming number of UW graduates as my colleagues at UBC. And I love them all, just like, and I also want to say that part of the joy of going to UBC was the pleasant, wonderful, and unexpectedly warm greeting I got from the entire UW community. And I realized that I was not just going to UBC. I had a big extended family across the Cascadia corridor. Anyway, when I talk about computer systems construed broadly, I'm going to take the first 5 minutes or so of this talk to give you a little bit of a soapbox about how I think about computer systems. And I actually think it's important because I worry a little bit that in our field we stand in little boxes that we never move out of, and I think that's really dangerous. So the way this talk is going to work is there are 4 parts. There is a little bit of philosophizing at the beginning that I will try to get through quickly, and then what I want to do is present 3 research vignettes. If I am going to claim to do computer systems construed broadly, then I should in fact present computer systems construed broadly, and I'm going to try to do that. What that means for you is that if you find at any point in the talk, other than the first 5 minutes, that you hate it, you can feel free to zone out. But come back and check in on the next vignette, because the next vignette might have something that interests you. And if you don't like that, then perhaps the third one will. And if none of them do, then you can yell at me at the end. I usually am happy to take questions in the middle of the talk, and I will encourage that. There is a bunch of material to get through, so I might also get a little bit anxious that I might not finish it, and so we'll try to balance those 2 competing forces, because in particular, the first vignette often incites lots of controversy and heated opinions, which I thrive on, but which might take away from the latter 2 parts of the talk. Once upon a time, when systems started, the question we were asking was, can you build a mechanical computing device? And in some sense, that was a wonderful world, because all of computer science and all of computer systems, for sure, was one big happy area that involved hardware and software and programming. But lo and behold, eventually, hardware and software became different areas. Hardware was often done in engineering. And even pretty early on, software broke into 3 areas. The database community split off pretty early, and the programming languages community split off pretty early, and many people just thought of operating systems as systems. And then the hardware world also seemed to break down at some point into architecture, and then special architectures or high-performance computing. And then networking happened, and operating systems suddenly became multiple areas. We had operating systems and networking, and then when you put the two of those together, you got distributed computing, but you actually saw the research happening in different communities, and the worst part is that those communities didn't always talk to each other. About 2 milliseconds after networking was invented, suddenly security became like a really big problem. What a surprise. And then at some point, so I spent the first part of my career in this uneasy valley between file systems and database systems because I was too dumb to realize that they were like different communities and different people did them. They all kind of seemed like data storage to me. And then eventually the storage community emerged, which made me feel a little more comfortable. But it took many years before the database people really realized they were doing storage. And so those communities are actually somewhat disparate. Scientific computing has always been kind of a thing of its own for some unknown reason. And then the oddest thing happened. We had operating systems, we had networking, we had distributed computing, and suddenly network systems became a thing because distributed computing was all about client-server, and network systems was really about different architectures. But this, I'm not really very quick, and so these always confused me that these were really different communities. And when I say different communities, these people don't always talk to each other. So I was once, and only once, asked to serve on a program committee in a database conference, even though the database community thinks I'm one of them. Anyway, and there was a paper submitted that I was very unhappy about because it had already appeared at SOSP, and it was essentially a rewrite just spun for a database community. And I pointed out to the program committee that I thought this was double publication. And the answer I got back was, well, our community doesn't read those papers, so maybe we should publish it anyway. No, I won. On the other side of the world, mobility became a thing that had both hardware and software components, so it became its own area. And then what we used to call sensor networks, we now call Internet of Things, because that's much catchier. And if you're going to build these little Internet of Things devices, you have embedded systems. And of course, we implement architectures out of VLSI. So what used to be like one big area is now at least 15, if not more, different communities that don't talk to each other nearly enough. If you take nothing else away from this talk, I want you to realize that this is actually not a good thing. This is kind of a bad thing because many people and many of us like get locked in these little boxes. And I encourage you not to get locked in a box because very often some of the most interesting and exciting work happens on the boundaries, on the lines. And I actually think the culture here, at least what I've seen, really encourages work that is on the lines and between areas. And I think that's a fabulous thing. And I would just encourage you to keep doing that and do it even more broadly. When I was asked to go to UBC and do systems, I said, cool, what does that mean? These are all areas where I can plausibly say I have done work. And if you add my colleague Ivan and the folks in the network systems lab, we kind of cover many parts of the box, but there are still gaps. So there's still room for more people to come play with us. Have I mentioned we're hiring? Anyway, we'll come back to that. And then, of course, because it is 2018, you can take any one of these boxes and sprinkle them with machine learning pixie dust. And you have new areas. And you can do that machine learning pixie dust in either of two directions. You can build systems that are better for pixie dust, or you can use pixie dust to make your systems better. And I would encourage you to do both of those. End of soapbox. That's what we do at UBC. I'm going to talk about 3 projects, most of which took place before I got to UBC because, shocking, I haven't done much work in the last 3 months that I've been. Turns out Canada's a different country. Like, they didn't tell me that. So first, I'm going to talk about what is arguably the most insane, crazy, and audacious project I have done in my career, the Automatically Scalable Computation Project. Then we'll talk about applications, runtime applications for data provenance. And then I will talk about something completely different, which are certifiably optimal rule lists. And ideally, we will get through all of these, or not. The Automatically Scalable Computation Project is the result of one of the joys of being a faculty member. So it turns out the best thing about being a faculty member is you get to work with really brilliant students. So one day, this first-year graduate student walked into my office, and he thought he had a Ph.D. project he wanted to do. In fact, what he presented me was a lifetime research agenda. And in fact, the lifetime research agenda is that we really, really ought to be able to take sequential programs and just parallelize them automatically. And it's really unfortunate that we haven't been able to do that yet. And I thought, this is very cute, and I don't want to dissuade a very excited first-year graduate student. The student is Amos Waterland in the big black font. But I'll let him work on this for a year, and at the end of the year, he'll realize that this is really not a PhD project that's going to happen, and then we'll go and we'll do real research. Yeah, instead, we now have this cross-university consortium. We have NSF funding. We've been responsible for a gazillion undergraduate senior theses that are in sort of this red font. We've had a couple of high school students work with us. We have many faculty involved, PhD students, postdocs, and I've actually talked about this project all over because I think it's amazingly cool and it actually kind of works. Or at least I will try to convince you that it works. If you put this in the jigsaw puzzle, and oh, by the way, the jigsaw puzzles are going to be your little messages that we've now entered another vignette, so if you zoned out, you should come back at least for a moment. This is part architecture, this is part scientific computing, this is part operating systems. There are actually some maybe distributed systems components to it, and it has ML pixie dust in it. Let's begin with the following question. Why don't computers get faster with practice? If you or I were to take up running and we did it enough, we would expect to get faster, but computers don't. So if I took a simple program, this is trying to compute the two factors of a very large semi-prime, i.e., hack RSA, and I ran it 10 times, what would we expect to happen with the performance? Well, in fact, nothing much interesting would happen. But instead, if I run this under control of the ask monitor, and I ask what happens over time, it turns out that the performance improves. Now, mind you, I'm running the same program with different inputs. So it's not like I'm saying, oh, the answer is 42, I'll just print out 42. No, no, no. This is with different program inputs. And it turns out that given the particular architecture on which we ran this experiment, about the best you can do is get a factor of a 1/3 speed up. So what is it that we're doing that is letting us run a program faster each time we run it? And that is what we'll talk about. In order to understand this, I want you to join me in a ridiculously preposterous little thought experiment. So let's take the memory and the registers of a standard single-core, single-threaded processor, and we're going to think of those registers in memory as comprising a state space, a really big state space on most machines. If we think of it that way, then I ask you the question, what does computation look like in this state space? And here's what I'm going to claim it looks like. You take this big state space and you initialize it with stuff, in this case, a program and its data. So for the rest of this section, you're going to have to bear with me. These are programs where we know the data up front. And the motivation for this comes from our colleagues in applied physics who really have these huge simulations and things where they have all this data up front. So it's not a preposterous assumption, even though it's not as general as we might like. And furthermore, some of the benchmarks are literally code that we just yanked out of their programs. We initialize the state, and then every time we want to execute an instruction, the state changes just a little bit. So if we load 0 into R0, the state is roughly the same. We've changed the value of the instruction pointer, and we've changed the contents of R0. Similarly, if I want to execute the add instruction, we change the state yet again. So each instruction is really just taking us a tiny little step in this really big state space. If I think of computation that way, then an entire program carves out a path in this really big state space. I'm showing you a 2-dimensional state space, but imagine the gazillion dimension state space that you get from all the registers in memory. If you think of execution this way, then I would claim there's an obvious approach to automatic parallelization. And it goes like this. Well, let's just cut the trajectory up into equal pieces. We'll put each of those pieces on a core, and then we'll execute all those pieces in parallel. And if I do that, yeah, that's pretty cute PowerPoint, isn't it? I won't tell you how long I spent doing that. But if I do this, I get perfect linear speedup. Why didn't we think of this, right? What's wrong with this picture? Is there anything wrong with this picture, or should we just all do this? You don't know ahead of time what the trajectory is, and so therefore you can't necessarily do this. Because if you did know what the trajectory is, I could do even better. I would just predict the final point, and then I would get infinite speed up, and we'd be even happier. So let's try something else. Let us start executing at the beginning of the trajectory. And as we execute, I'm going to watch the execution, and I'm going to try to build a model of the execution such that at some point, I will be able to make predictions about places I might be later in the execution. And some of those predictions might be really bad, and some of them might be really good. But once I've made a bunch of predictions, and so these represent probability distributions of places I think I might be, if I were to do that, then I could kind of do the same thing I did on the other slide, which is say, OK, let me allocate a bunch of cores. And each core is going to pick one of those predictions and start executing from there. And so each of those will execute a little trajectory from that spot. Meanwhile, the main program is going to start chugging along, and periodically it's going to stop and say, has anyone seen this spot in the trajectory? And in this case, no one has, so it keeps going. How about here? No, no one's seen that either. But lo and behold, we get here and say, has anybody seen this one? The answer is yes. When you get a hit, you then say, great, where did you end up? And you immediately fast forward to the end of the execution. And so lather, rinse, repeat. We keep doing this. When we get a hit, we zoom ahead. So this basically depends on our being able to make accurate predictions and then use those predictions. If my predictions were all accurate, I get that perfect linear speed up. If, in fact, my predictions were wrong, ideally I don't run any slower, but I don't get any speed up either. Before I tell you how we did this, I just want to convince you that it does, in fact, work. So this is a benchmark result from an icing simulation. This is an energy computation. This is the code we literally yanked away from our physics friends because they thought we were trying to help them. And we did actually help them. So the problem being solved here is we have a linked list. And again, we did not make this up. This is their code. They had all these electron configuration or molecular configurations, and they wanted to find the lowest energy state. So they'd put them all in a linked list, and they were iterating over them and computing the energy, which is super expensive, to find the fastest one. And one of their great frustrations in life is that they would periodically write grants and get big new high-performance machines. And every time they did that, they had to rewrite all their software. And they were really, really tired of rewriting software because unlike us, they thought their job in life was to like do physics research, not computer science. Anyway, this was their code. The black line would be what you would get if we scaled perfectly. Given the overheads of our implementation, the red line is the best you could possibly do on this particular problem on our platform, and the blue is what we actually get. So what this says is with 42 cores, which is how many we had at our disposal, we basically got a speed up of 22, which is amazing. If you look at any of the parallelization literature, unless the program is just embarrassingly parallel and has been hand optimized, you don't get 50% of all your cores at numbers of 42. Like, this just doesn't happen. So this is kind of cool. And furthermore, remember I said it's a linked list. Dynamic data structures are not one of the structures that most conventional parallelization techniques handle very well. So this is what convinced us that this was kind of cool. Let me give you a little intuition. If I showed you this trajectory and said programs look like this, how many of you think you could build a predictor for it? Come on, you're all UW people. You can build predictors. If I showed you this one, how many of you think you can build a predictor for it? Good. Turns out many of the real programs we look at look kind of like this. So you can look at that and say there is a pattern. And the goal in life is to figure out the pattern sufficiently that we can make some reasonable predictions. And that's going to be the name of the game. I'll present this in two parts. I'm going to show you a general framework for how we think about the problem. And then I'll talk about a specific implementation. One of the beauties is that the framework is totally modular. And so you can pick any particular area and say, ooh, that's kind of interesting. I wonder if I could build a piece that worked better there. And you could do that. So if you're interested, come play with us. We start out with some kind of execution engine that implements at least this abstraction of trajectory-based execution, that we go from state to state to state. Then what we're going to do is feed the vectors that represent these states into something we call a recognizer. The goal of the recognizer is to figure out where in the program should I make predictions. Hint, like inside loops is a good place. But where inside loops? The beginning of the loop, the end of the loop, the middle, where should I make these predictions? That's the job of the recognizer. Once it knows where to make predictions, that goes back to the execution engine, so that the execution engine can A, hand over new versions of the state, and B, check to say, has anybody been here? Once we build a model, then we will generate predictions. And once we have predictions, we have to decide which of those predictions to allocate to cores. And once we've allocated them to cores, then we're going to send them off for speculative execution. At the end of a speculative execution, we take the results and we put it in a cache. And the cache is what we consult and say, hey, has anybody been here? And if the answer is yes, we get a hit. So this is the general structure. So one can do research on how to implement trajectory-based execution efficiently. You can spend an infinite amount of time trying to figure out how to implement a trajectory cache. Trust me, we did. You could also spend a bunch of time deciding on models and how to build the models and how many to build and stuff like that. So there's projects here for everybody, and we even have some theoreticians at BU who are working with us to try to answer what became known as the Margo question, which is, so for what class of programs does this actually work? And is that class bigger than the class of programs that compilers can parallelize? And my wonderful colleague has answered the question. The class of programs for which this works are those that have points that exhibit low entropy over execution. OK, I agree with him. And now our challenge is, could we translate into something that is actionable? And so that's our current battle. We've built 2 full implementations of this. I'm only going to talk about one. The first one I call Scaliask, because what it just does is it demonstrates the scalability that you can get. In reality, it uses a software-based virtual machine. So it's what we call pig dog slow. And therefore, you don't get real speed up. But we show incredible scalable potential. And then we have a real implementation that gets speed up relative to bare hardware. And that's SpeedyAsk, and that's what we'll talk about. How do we build this beast? Well, I call it the fancy trajectory-based execution engine. We call it an x86. So runs on real hardware. The recognizer is going to be an offline recognizer. So our initial scalable one, we did all the recognition inline. In this current case, we've tried, I think, 3 different recognizers that all work to varying good degrees. This is finding where to build models. We have one now that works really, really great, but it requires that you run the program a couple times in advance. So it's not really an ideal inline solution, but again, it tells us that there's a there. We've tried a couple of different predictors. You know, because 2018 Pixie Dust, we started with neural networks, and it was like, ooh, the networks work really well. And then one of my wonderful undergraduates said, you know, we're predicting binary bits. Why don't we just build decision trees? Oh, it's actually kind of a really good idea. So it turns out we build decision trees now. He's now a Ph.D. student at Stanford. Our allocator is really, 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 really stupid simple, which is if we have n cores, we try to predict timestamp n+1, n+2, or I'm sorry, you know, 1 step in the future, 2 steps in the future, all the way up to n steps in the future. Not very tricky. And then our speculator is, in fact, a bunch of x86s. We'll add a little bit of magic there in a minute. And our trajectory cache is a kind of hash table. And this is one of those cases, and I'm thinking many of you who are like 3rd and 4th and 5th year graduate students have run into this, where we spent way too long trying to be way too smart. So we spent like 2 years trying to come up with the right data structure for this problem, and I'll explain the problem later. And then same graduate student who figured out the decision trees came up with a much, much, much better solution that sort of sidestepped the entire issue. So this think outside the box metaphor hugely important. Yes?
Are you caching the entire trajectory or just like the start and end points?
Hold that thought. We're going to get there. I'm going to explain exactly what we're caching. All right. So the technology that we're going to use to make this happen is PIN, which is a dynamic binary instrumentation tool. And we're going to use it in two ways. So the general way that you use PIN is you take a program, you instrument it, and what that says is, I would like to inject instrumentation after certain instructions. And then you build little PIN tools that execute something every time you hit one of those, and you process the data to do something interesting. The first place we use it is this offline recognizer. So what we do is we instrument every backward jump instruction, i.e. we look for every loop, and then we run the program once, and we count how many times we hit each of the jump instructions. And then what we're looking for is we are looking for places in the program that are hit at least a certain number of times, i.e. we want it in a loop so that you can get some benefit from speculating, but we want the minimum number that crosses that threshold. Because what we want to do is we'd like to make big, long speculations, right? If you think about what hardware does sort of small-scale speculation. We're doing large-scale speculation on the order of hundreds of thousands or millions of instructions. And so what we want to find are places in the program that are, in fact, hit repeatedly, but that there are long periods between them. And so we just directly measure it with a couple of preliminary runs. The other place we're going to use PIN is when we do this speculative execution. And so this is starting to address the question you asked, and then we'll go into it in more detail in a couple more slides. So we start, and we take the user program, and we put it on one core. That's our main thread. And we run it under ptrace, so that ptrace can say, please stop every time you hit my recognized instruction pointer. Meanwhile, we're going to create some slave processes to run as these worker threads. So we spawn off PIN. PIN, in turn, spawns off the worker processes. And the worker processes have PIN tool interventions at every load and store. So we need to track all the data dependencies so that we're not caching full trajectories. So what happens now is when the user program, the main thread, encounters the recognized IP, it triggers a breakpoint. ptrace says, OK, send a copy of your state off to a worker. And the worker can either execute from there, or the worker can use that state to build a model, or the worker can do both. So in our current implementation, workers both build models as well as make predictions based on those models and spawn off speculative threads. Now, if you don't do anything fancy in the speculation, yes, question?
Just a quick clarification. So in the 22x parallel speedup, is the startup overhead for PIN to translate all the code into its code cache included in the 22x?
Yes. Yeah, so the overhead, the difference between the black line and the red line is the PIN overhead. Now, if you don't do anything fancy during speculation, you end up with two problems. The first problem is the one you alluded to, which is that your cache are these enormous bit vectors. That seems like a problem. But the other is that your prediction problem gets pretty complicated because it is conceivable that every bit in the predicted state depends on every bit in the input state. So you get a really, really big tree. There's a little bit of a intellectual debate that goes on between me and my student in that, we kind of know things about the state, like, it's broken into 64-bit chunks, or maybe it's 32-bit chunks, right? Like, there's some structure to the state. He's really wedded to, it's a bunch of bits. We know nothing about the structure other than where the instruction pointer is. So we're actually solving a harder problem than we need to be. And this is sometimes when you bite your tongue and say, OK. And in some sense, the goal here is that we know there's a lot of benefit you can get if you know about the semantics of the program, right? Everywhere from the language down to the architecture to everything else. You can think of this as fundamental research, which is how far do we get if we don't leverage any of that? And then there are an infinite number of incremental projects you can do, which is say, ooh, what if we know there are registers? What if we know that there are sets of registers? What if we know there are objects? And you can sort of incrementally add knowledge about the structure of the program. But if the fundamental idea doesn't work at all, maybe it's not worth doing that. And you're back to sort of compiler parallelism, which is a fine thing. OK, so the question is, what can we do during speculation to make this prediction problem easier? And so this is now going to get to your question, which is, what does a cache entry really look like? Here's what we can do. We're going to instrument all the loads and stores. And what we're going to try to do is capture every bit dependency in this execution. So right now, we will assume that our entire speculation is a single instruction which adds 8 into some address A. And what we'll do is we'll say, OK, S0 is, in fact, our state. And we're going to keep a mask that says, what are all the bits that get read during this speculation? And for that mask, what are the initial values we ever read from those bits? So we copied all the values from the state that we're in. Then we execute the instruction. And we say, now we need to compute the write set. So every bit that gets written shows up as a write mask. And the values that get written show up as the write values. And we're going to continue executing. And for every instruction, we may add to the masks, and we may update the values. Once you have a value for a bit, you never have to update it. For the write bits, every time you update a bit, you have to write it, so that you end up with the last thing written and the first thing read. And over the course of the execution, what this will give you is, here are the bits you care about, and here are the values that you have to match in order for this to be a hit. So this set of 4 vectors is a cache entry. And so it is much smaller than the entire state. It is only as large as the number of bits that were read and written. Does that now answer your question? Great. What we've accomplished by doing this is we've taken a single speculation and we've turned it into a family of parallel speculations. Right? So these are paths in the state space that are computationally equivalent. Think of it as memoization. This is actually a form of speculative memoization. Right? If your input parameter are these bits in these positions, then we can tell you exactly what your output parameters are. It doesn't matter where you are in the program. Right? If you're going to call a multiplication function, you can call it from anywhere, and the result of multiplying 4 by 3 will always be the same. It's exactly what we're doing here. If you're executing a loop, and we capture everything you read in that loop, then we know exactly what the state will be when you're done. Does that make sense? Great. So now what we've done is we've taken that full n by n predictor and turned it into a much, much sparse predictor. So A, they're much smaller. B, they're much faster. And life is good. Therefore, what our cache is now is a collection of these cache entries. When confronted with a state, you say, OK, look at my read bits. Does it match? Those are the bits I have to match on. So now I look at the values. I compare them to the values in the cache entry. In this case, they don't match, so it's a miss. I try the next entry. You need to match on these bits. So we look at the values. Aha, they match. Now I need to construct the output state. Where does it come from? Well, I know that it's going to include the values from the write set. So all the values that are in the written entry just go directly down. Where do I get the values for all the other bits? Where do the black bits come from? SN, good. Right? So these are the ones that are just going to come from whatever state I started in. Because they didn't get written, they don't change, I just copied them down. So this is what lets us keep. So we have programs that are 10 to the 9 or 10 or 12 bits. And our cache entries tend to be on the order of 10 to the 3 to the 4 to the 5. So this is why we get the low entropy statement. Right? If you can find these narrow points in the program, then you have a prayer of making good predictions and of being able to use this stuff. So I mentioned the lookup problem in the cache. If you step back abstractly and ask what we're doing, we have reasonably large bit vectors. Some of the bits matter, and many don't. And the bits that matter and don't vary depending on the cache entry. Your homework assignment is to build a data structure to implement this. And we spent 2 years building all sorts of fancy trees and tries and gazillions of data structures, all very clever, all somewhat promising, all really complicated. And then Peter Kraft said, you know, if I look at the active register set at the beginning of a speculation and I hash the values, turns out that's a pretty unique key. I'm like, really? He's like, all the programs so far. So in fact, that's what we do. We take the register set, the set of active registers, we hash their contents, we use that as a key, and if that hits, then we compare the full vector, and voila, we have a cache hit really quickly. I would have given him his, bachelor's degree on the basis of that alone. All right, so that's the cache. As I said, our allocator is really dumb. If we have 3 extra cores, we put now, assuming there was no overhead, what you would do is you would run the first time step on the main core, and then you would have the other workers execute the next time steps. When the first worker finishes, right, so when we finish executing, I'm not going to even bother. OK, when we finish executing timestamp 1, 2, 3, and 4 have finished. We look in the cache. We should get 3 hits in a row. And then we can go ahead and do 5, 6, and 7. And we get perfect linear speed up. So this is assuming that A, there's no overhead, and B, our predictions are all perfect. In reality, there's a variable amount of overhead. So this doesn't quite work. So if, in fact, the overhead were 50%, you would not want to be speculating time steps 2, 3, and 4. You would instead want to be speculating, time steps 3, and then probably time step 5.5, or time step 5. And so you have to, and that's where the red lines in the results are going to come from, right? This is the overhead. And as you'll see, it's going to vary a lot. This is the result I showed you earlier. It's a pretty small program. So both the pin overhead and the overhead to carry the state and create these snapshots is pretty low. In contrast, here is a matrix multiply. Now, I understand there are super fast algorithms to parallelize matrix multiply. I get that. But what you need to get is that this is an unmodified, stupid implementation of a matrix multiply that we parallelized automatically, which is sort of cool. The bad news is that the best we can possibly do is like 5 out of our 42 cores. And that's because this is a 4 gigabyte matrix. And you have to copy 2 of them. And so the time that it takes us to copy the data is actually huge. And that's where all that overhead comes from. The good news is that we're still getting about 50% of the possible speed up. So we're able to make decent predictions. My hypothesis is that we could actually do a lot better with some fast checkpointing technology that we haven't implemented. And there's about 12 other gazillion ways that I think we can improve that. So I have a bunch of benchmarks. I'm happy to talk about you with this later today or tomorrow. But at this point, I want to stop this and go on to vignette number 2, unless I have a couple of questions. OK, I'm just going to take 2, because there's more fun stuff to do. Yes?
When you run your couple of example programs at the beginning, sort of how lucky do you have to be to get good inputs that are going to give you sort of results typical of most cases of running your program?
So it turns out it just works, because pretty much everywhere in the loop is almost equally good, as long as you're not stupid.
How much does the energy utilization go up?
Yeah, energy. So we are supposed to look at energy, and we have not yet. Absolutely. Let us now talk to something completely different. So I've been doing data provenance for a long time, so long, in fact, that at one point I said, we've had 0 impact. I'm not doing this anymore. And then I got 2 grants funded. I'm doing data provenance again. This time, although it took me 2 years to get smarter, I'm trying to be smarter. One of the things I love about this project is that we have 8 authors on this paper from 8 different institutions around the world. Interdisciplinary research and collaboration is fabulous. If we put this in the little jigsaw puzzle, this was the note to wake up, then this is a network system problem. We've applied it to some security things, and because, OS is always good. Here's the big idea in one slide. When people capture data provenance, which is this history of how a piece of data came to be in its current form, the standard structure, an architecture of these systems is that you capture the provenance, you put it in a database, and then you write applications on that database. The problem is that there's a big delay between the capture and the analysis. And so if you want to do things in real time, like, oh, by the way, something bad is about to happen on your system and I want to stop, this doesn't work. So the big idea here is we're going to rearrange the order. We're going to capture the provenance, we're going to analyze it in real time, and if you want to store it for later analysis, have a good time. Furthermore, there's a new little dotted line, which means while you analyze the provenance, if you want to add things to the provenance stream, you can do that too. What this enables is that instead of doing static graph analysis, which you traditionally do for these queries and analysis, you get to do streaming graph analysis. So you get to learn a whole new area of research. In historical applications, you could detect things that had happened in the past, whereas now we can actually prevent things that are about to happen. And that broadens the class of applications you can do. The other interesting part is that the static solutions are all, execution time is typically a function of the size of the entire provenance graph, which is, not to put too fine a point on it, enormous. So that's bad. Now you can do things in sort of the complexity of the function you want to implement, which we have is like 10 lines of code, so that is good. And furthermore, provenance is immutable for good reason in many architectures, but we can actually add to the provenance. We don't throw it away, but we can add to it. A very short overview of provenance. It comes from the art world. So if I tried to sell you this fine painting, you might want me to prove where it came from before you paid me millions of dollars for it. And in the digital world, data also becomes more valuable if I can tell you how it was produced and where it came from. So the traditional models of data provenance have entities and relationships. The entities are things like agents, the people or programs that make things happen, the activities, the things we do to data, and then the data itself. And then we connect these things with relationships. And the relationships all have lots of interesting names that are defined by a standard model. And I could rant for an entire other talk about how awful the current model is, and it doesn't actually provide any utility, but I'll save that for a different talk. And you can collect provenance in all sorts of places. So languages, database engines, operating systems, workflow systems. We will focus on operating system provenance. The tool we've built is called CamQuery. And the idea is that here's the old architecture, and here's the new architecture. So what we're going to do is we have a loadable kernel module called CamQuery that sits in the operating system. And instead of this delay, what we do is we use LSM hooks and net filter hooks to capture provenance. And because we're using the LSM hooks, we know certain things about the completeness of the provenance, in particular, that every information flow is actually captured in the kernel. That wasn't supposed to happen. Let's try this again. OK. So we use CamFlow, we use NetFilter and LSM. Great. And then what we do is we take the query and analysis and we drop it in the kernel. And you can either build it directly in the kernel, or you can download it as a loadable kernel module. And then if you want the data for later analysis, you can do that by exporting it up to user level and storing it in a database. What this enables us to do are some applications that have been either hard or expensive in the past. So the first one is data loss prevention. You have confidential data on your system. You don't want it to get off the system. And so you capture the data provenance. You assume that someone has marked data as confidential, and then we track the information flow. We've built intrusion detection systems. And then we've built all sorts of other applications that use data flow, like, only certain kinds of users are supposed to get certain kind of data. We can show that the data hasn't been modified since it was initially created, things like that. And then we can also enforce constraints on the way information flows around the graph. So, information from nodes of type A must never flow to nodes of type B. We can enforce that in real time. I'm starting to go a little faster because we don't have a lot of time left. So what does an application look like? The bad news is that right now you write C code for your applications. That's unfortunate. I actually had some undergrads who are working on a graph query language that will make this better. The good news, though, is you write 3 functions. You write an initialization function, and then you write a function that says, here is what you should do whenever a node gets a new input edge, and here's what you should do whenever a node gets a new output edge. So this is the entire application to track information loss. So I have a bunch of data that's marked confidential. My goal is to make sure it never gets transmitted off the system. So what I do in initialization is I go and ask, what is the label that says confidential? I get a value, and I just hold on to this so I can use it later. So that's, 0 time. Whenever I see an incoming edge to a node, I'm going to ask, does that edge have a confidential label? And if it does, then I will make sure that I propagate that confidential label to the node that is getting this edge. So I'm basically processing the information flow. And if that node happens to be a network socket, then I say, no, 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 you do not get to put confidential information there, and I prevent the flow from happening. Right? You can't do that in any other provenance system of which we're aware. And finally, when you get an outcoming edge from a node, you look at the node and you say, is it confidential? And if so, make sure I propagate that confidential label to the edges. So that's all you have to do. The rest is boilerplate. If you wanted to change this query from running in the kernel to running outside the kernel, you lose some of the real-time nature of it, but it's about 3 lines of code change. Instead of kernel query, you say what kind of mechanism you want to use to send the data to user space, and then you add the details of that at the end. Voila. As I said, we use LSM and net filter hooks, and that guarantees that we capture all the information flow, and there's actually some formal proofs that confirm that. The only other super interesting part of the implementation is that you have to do some form of cycle avoidance, which many provenance systems have to deal with. So every time that a process consumes shared state, you're creating an edge from the shared state to the process. And then when the process transmits shared state, you have an edge from the process to the shared state. So what happens when a process both reads and writes data? So when we read it, we get an edge that looks like that. And if the process then tries to write the same file, we would create a loop. Loops are bad. Provenance is sort of causal history, and so loops are bad. So instead, what we do is we create a new version of the file, because the provenance relationship is that the version of file F at the time it transmitted to provenance P is kind of different from this version F2, because F2 has been modified by whatever happened in P. So they really are fundamentally different objects. They just have a relationship of versioning. And if you do that, then you get rid of cycles. There's a ton of performance data where the higher order bit is really, this is really fast and doesn't slow things down. So the big message here is that we can now do really, really interesting applications in real time, and we can actually prevent things from happening instead of just telling you what happened after the fact. So this is pretty cool. We think there are also many, many more applications we can build on this. End of vignette number 2. And now for something completely different, let's go to vignette number 3, which will require a bit of technical magicianship here. And I am going to let my colleague, Cynthia Rudin, give you a 2-minute overview of Certifiably.
For real machine learning problems, is it always true that a complicated black box model will outperform a model that is interpretable? Of course not. In fact, for many real applications, there is a large set of almost equally accurate classifiers, including some that are interpretable. The challenge is how to find these accurate yet interpretable classifiers. For many years, greedy methods like classification and regression trees, associative classification methods, and decision list methods have been used to find interpretable logical classifiers. But these methods do not always perform well and often do not actually provide interpretable models. It could be that no accurate yet interpretable model exists for your problem, or it could be that the interpretable model exists, but that the greedy algorithm couldn't find it. After all, the space of logical models is exponential in the number of features. But how do you know which it is? Is it that no accurate yet interpretable model exists, or that your algorithm just couldn't find it? Maybe an accurate yet interpretable model actually does exist. Luckily, as it turns out, to construct some kinds of models, and in particular rule lists, the part of the space we need to search isn't as large as it seems. In this paper, we produce an algorithm that actually optimizes over the full space of rule lists. The algorithm is called Certifiably Optimal Rule Lists, or CORLs. rule lists are a kind of one-sided decision tree. If a very simple rule list model exists that predicts accurately on the training set, this algorithm is guaranteed to find it. Here is an example of a rule list generated by our algorithm. This list predicts whether someone will be arrested within 2 years of being released from prison. There's nothing unintuitive here. It finds that prisoners with longer criminal histories and younger prisoners are more likely to be arrested after they are released. This model looks like a heuristic for predicting recidivism, but it is a full-blown predictive model that was certified within 2 minutes to be optimal according to a regularized empirical risk on the training data, which was the ProPublica dataset on recidivism. The algorithm uses a combination of tight bounds to use in a branch and bound algorithm, fast bit vector calculations, and some very useful data structures. We use a prefix try to keep track of all the rule lists we've tried so far. We prove that we can find any optimal rule list, starting with the rule list we have at the try in any time. We have a symmetry-aware map to keep track of the optimal permutation for any given set of rules, and a queue of rule lists to look at. Once the queue is empty, we've searched or eliminated the whole space. Corals is a good competitor for decision tree methods like CART. The code for Corals is publicly available.
The reason I like to show that video is actually threefold. So one reason is that, come on, there we go. So one reason is that KDD requires that you do, or strongly encourages you to do a short video that actually gives an overview of your paper. And that exercise of doing that is incredibly important. And it's a great marketing tool. People who won't read a 14-page paper will watch a 2-minute video. I would actually encourage you all to do 2-minute videos of your published work and use that to publicize your work. Number one. Number two, that video is a team production between Cynthia Rudin, my collaborator at Duke, me, who did the PowerPoint, and my daughter, who did the video production. And so I like to show that. And there was a third reason that I've now forgotten. So this project is a collaboration between me and Cynthia is the brains behind it, and I do a bunch of the implementation or ask stupid questions, which turns out to be really useful. It's also, we have one of everything. So Elaine was a postdoc at the time, Daniel was a graduate student, Nicholas was an undergrad, and we have 2 high school students who've worked with us on this and made meaningful contributions to the project. And I also think that's pretty cool. The other thing is that it doesn't really fit neatly into my jigsaw puzzle. So throw away the lines and do whatever is interesting. One of the reasons I find this really appealing is that I think while deep learning is amazing and finding pictures of cats on the internet is lovely, there are applications that have perhaps more social relevance where interpretable models are really important. And I can go off on a tangent about interpretable versus explainable, but I will spare you that. So I actually think that these sort of interpretable models are really important for things like loan origination and the Justice Department and all sorts of other places where I want to know, like medical diagnosis. Take the blue pill. Why? Right? All right. So we are almost out of time. I think, what's the important thing to talk about? I'm going to assume you know what a one-sided decision tree looks like. The real important takeaway from the algorithm is the following. I like to describe my work with Cynthia that what we do is we take intractable problems, we solve them to optimality on laptops for real data sets. That's kind of cool. The insight is that she's really good at figuring out how to use branch and bounds mechanisms and develop new bounds on ways to throw away parts of the search space. And historically, computers weren't fast enough to do anything with that. But if you take those bounds now on today's generation of hardware and you look for the right data structure abstraction, suddenly things that didn't perform well can perform really well. So, we all in systems take bit vectors for granted. But a lot of algorithms people think about set membership and set union and set things. Turns out you can implement those in bit vectors really, really efficiently. This custom trie is not any data structure you can download from an implementation, but in fact, if you know something about tries and trees and caching, you can do that. And then most interesting, one of the big takeaways from that Ask project is that if you do computation in advance in a way where you can reuse it later, you can make things faster. And one of the insights that we keep bringing to these problems is this idea that we can cache computation. And so in some cases, it means keeping track of certain bit vectors. In other cases, it means building other data structures. But it turns out that in computer science, we've spent a ton of time thinking about caching data and a lot less time thinking about caching computation. And so one of the big insights that we really focus on in this work is clever ways to cache computation. And I think that's a huge tool that is perhaps overlooked. So on that note, I am going to jump to the end of the talk through all the animation that's really pretty and I would love to talk to you about. OK, and so thank you. Remember, we are hiring. We're still taking applications for both research faculty and teaching faculty. Get your little QR code readers. And I'm also looking for both postdocs and students, so send me email. And on that note, it is exactly 4:30.
So both of the programs that were shown in the first part, the first vignette, were C programs?
Yes.
Did they use dynamic memory allocation at all?
Oh, what a great question. Yeah, the answer is yes and no. We hacked our own allocator so that we could make it work.
I guess I would take some, the follow-up there is I would take some issue with the portrayal that language level work is sort of an add-on that incrementally improves on this effort. Because it seems like this approach would have a great deal of trouble working with something like the existing JVM.
Existing what?
Well, if you try to run the tool on the JVM, what happens?
On the JVM, yeah. So on the JVM itself, it's probably, so we haven't tried this. We get asked this question about both JVM and Python as well, because the program, if you ran the JVM with the running the program you care about, then I think maybe it would do okay, but I don't know. We haven't tried it. Running huge programs on it is really hard, and the JVM is really huge. So I don't have a good answer to that. It is something we keep thinking about. Like, what if you have an interpreted language? How would you make that work?
Well, I'm more thinking of just that how dynamic memory is. A given memory address has no stable meaning.
Right.
So it may be that a language level story is necessary to get off the ground at all.
Yeah, and that could very well be true. And as I said, this is an internal group debate that goes on a lot. Other questions? Yes?
So, I think certified the optional rule list. Something I was wondering about was, so like, there's a lot of other types of classifiers. Are you using rule lists like for their simplicity? Like, would this work on other types of classifiers?
So glad you asked that question. So we started with rule lists because when I first met Cynthia, she was doing scalable Bayesian rule lists. And so we started working on that. We now have a project where we're trying to build optimal decision trees. The search space is way bigger. We have made really great progress. We're just about ready to start writing that up. So the answer is yes for decision trees. We've also looked at, and the decision trees really grows very much directly out of corals. We're also looking at linear classifiers. And we are not quite as far along on those yet. But that's a case where some interesting pre-computation and computational caching appears to be very promising. So we hope to have that work done pretty soon. And what we tackle next will largely be dependent upon what Cynthia says. Hey, I think we can do it here. She has grand ambitions. She more recently said, let's look at SAT solvers. I'm like, OK, let's look at SAT solvers. But one of the reasons I love working with Cynthia is that she is fearless. And it's been a ton of fun. So again, look for collaborators who do stuff really different from what you might do in your daily life. Yeah, and Amina, stop laughing about the SAT solvers. Yeah, I started out with the answer like, I know nothing about SAT solving. She's like, either do I. We should learn. And I'm a big fan of that. Here and then here.
In your jigsaw puzzle of how systems has gotten split up, and your comments today, which maybe add the 16th piece of like systems for machine learning, what other things do you see getting added on to the jigsaw puzzle in the near future, assuming we don't reverse this trend of breaking ourselves up into boxes.
So optimization in general is something I've usually ignored and stayed away from, but lo and behold, I'm now convinced that it's kind of cool. You know, my attitude is whatever strikes your fancy and looks really interesting, we can cram in the box. I think, you know, my new definition of systems is if I can programming something around the problem, then it's systems. So that, you know, makes room for computational biology and genomics and pretty much any field of human inquiry. So I've decided that I'm not letting myself be boxed in anywhere. We did a seminar on accountable systems, so we're also talking to lawyers, right? How do you build systems that actually ensure accountability? Shockingly, this workshop was held 2 weeks before GDPR went into effect.
Yeah, so it seems like the combination of like, this is on the first product, the fact that it's operating over just this sort of black box like program and the sort of the modular nature of it means that like, it seems like there are maybe a lot of opportunities for like doing some kind of static analysis on the program and then optimizing something. Is there a particular version of that that's most exciting, like a particular spot on the pipeline that you think could be best optimized with some kind of static analysis?
So there are huge numbers. What's most exciting, I think the real question is, so I'm going to tell you one story and then I'll answer your question. So the one story is when we were still using the neural networks, we made a mistake. We built a network on program A, and then we ran it on program B. And it sort of worked. So we were, like this was really weird. What that tells me is that the model was actually learning something not only about the program, but it was also learning something maybe about the compiler and the libraries. But why should it have to learn about that? We have compilers and libraries. So I actually think if I were going to do a next generation of this project, as in not try to push this and really understand the fundamentals, but kind of try to build a new one, it would be let's take the state of the art in language-based parallelization, right? And we're still not going to tackle Java and Python, but let's take language-based parallelization in C or C++. And let's figure out where that breaks, and then see if we can interject ask techniques. And I am pretty convinced that by doing it that way, we can sort of prove, and I use that lightly because I don't know how formally we could do it, but I think we can prove that the class of askifiable programs is bigger than the class of compiler parallelizable. And we could do that practically by demonstrating it. But I also think, I keep working on sort of with the folks at BU on figuring out a way to really accurately define this class in a complexity class sort of way. And you know, we've done a bunch of stuff in expressing these in terms of Boolean circuits and stuff like this. So this is another one of these cases where not just being a broad systems person, but being a broad computer scientist is really important, right? So I have spent time wrapping my head around things like Boolean circuits that I really don't think much about in my day-to-day systems life, but figuring out where the right areas in computer science are to pull the right tools to be able to make some sort of formal statement about this is one of the more interesting problems, actually, which is different than the one you asked about. Oh, and there's one more question.
I was actually going to follow up on that because I think it's sort of interesting. The Margo question is you put like, there are a lot of problems for which the problem is not mundane, but a particular input, or like that a very common input might be mundane. So it's easier to predict for certain inputs than others, and that's really hard to state as a complexity class.
Right.
It says something about the shape of the problem or the trajectory of a particular input that's easier to predict.
So
how would you incorporate that?
I don't know that we've encountered places where the input actually changes the predictability. That doesn't mean they don't exist, but I don't know that we've encountered them, so we haven't really thought about that.
Like an NP-complete problem or something where you might have an easier time predicting a mundane graph.
Fair enough. Fair enough. And one of the other things I want to do actually is take something like, oh, I don't know, RSA encryption, which you better not be able to predict anything about that algorithm, I think, and see if we can. Because that would be really interesting.
Okay, let us thank Margo, and we'll join you.